Here it is, Applied Houdini Volumes 3 Version 2, Rendering and Sparse Simulation. In this lesson, we're going to talk about how to make a detailed, colorful, and fast smoke simulation by taking advantage of the Sparse Pyro Solver. We'll start by sourcing our smoke with a particle simulation and see just how the Sparse Solver works to help us achieve high-resolution results faster. We'll go over the most common types of lights and how they work with volumes, which we can then further control with material settings. We'll also cover a lot of universal volume rendering concepts and how we can apply them to Mantra to both iterate faster interactively while also making efficient high-quality renders. Finally, these images will be manipulated post-render with Houdini's own compositing tools to make our final images. Run better sims and understand more deeply how volumes are shaded and rendered today with Applied Houdini. Alright, so I'm all caffeinated up and hope you are too, so let's do new project and call it something like Volume 3, or no, Volumes 3, Volume 2, or Version 2, whatever. Save as, go to job, call it something cool like colorful smoke. Version 0. We're going to talk about a lot of stuff today. We're going to talk about colorful smoke. We're going to talk about rendering. Talk about the Sparse Solver. It's going to be cool. So we saved our file. Let us change our frame range. If you're feeling crazy, do 240 frames. Why not? I can't stop you. I'm going to do 120 frames because I don't feel like waiting for 240 frames. If your computer is slower, that's fine. Do even less. Do 96 frames or whatever. We'll probably not want any less than 96 frames, but you know, every frame more is a simulation frame and rendering. Rendering will take actually probably a lot longer than the simulation. Let's put our camera such that the x-axis here is going from left to right. I want to look straight down the z-axis. I'm gonna come all the way back here to. I want to look kind of up at it. I want to be kind of close to the ground so we can see like a ground display of fireworks. Press Control click on the camera. These are all fine. I mean, just get close enough to it. I'm going to kind of make these into prettier numbers maybe so you can just follow along at home if you want, but obviously it looks pretty much the same as that. So we got our camera and we got everything. So next chapter. And here it is. I loaded it into mplay, the final result, and it looks really cool. We really pushed it quite far in the very end too. I mean, this is the culmination of so many push it things. Like we started with, it was a particle sim, And then the particles turned into sources, and then we noised up the sources so that we could get an interesting sim. And the sim ran fast because we used the sparse solver. We made it colorful by adding color and then telling the solver, hey, you should pay attention to this color. We learned about the sparse solver and some of its shortcomings and some of its benefits. What else as I wrap this up? What do we do after that? Oh yeah, we actually put materials on it. We learned about the lights. We learned about render settings for rendering it quickly, interactively versus rendering it nice when we're actually done with it. And then we learned how to break that up into the constituent image planes so that you or your compositing buddy can then put it together and continue to make changes quickly or to tweak it to get it to actually integrate into a scene. Even last minute decisions that we made here, like, hey, make the smoke brighter, but bring down some of those areas that are too bright. Hey, these lights could be brighter here. Maybe we'll change the color. Maybe we won't. You were there. It just happened. So that's it. This is it. Looks cool. And I hope you liked this update, which was really in many ways a complete redo and is completely different than the old volumes 3 in almost every conceivable way. Yeah. All right. Well, until next time, enjoy the cool smoke trails. And because we are going to talk about compositing, and compositing is part of life and visual effects, we're going to talk about how to separate this out into individual elements so that you can control individual lights properties. You can control individual light scattering through a thing. There's a lot of ways we can break it up. I can say, give me a plane. We're going to call these planes, meaning an image plane that just shows the illumination of these lights. Give me a plane that just shows the illumination of the environment light. Just give me a plane that just shows me the secondary scattering, which we haven't actually enabled yet, of one of those lights, and so on. So the way we turn that on, it's pretty easy. This is going to get very specific to your renderer, probably, but in Mantra here, it is the images thing, extra image planes, and I'll pause this here. You can choose one of the ones from here. I like to just do extra image planes plus. What I'm interested in is direct. So these lights know what they're doing. They know that they're contributing direct lighting, or if they're contributing indirect lighting, or 100 other things that you can see listed here. But one of the most commonly used ones is direct here. And so if we look in here, we now have C, which is the actual total image, C for color. If we go to direct, okay, this is the direct lighting is essentially the overall image. So we don't really see much of value yet with this extra image plane. But if I go to light exports, I can say export variable for each light. Okay. So now what happens is we have an env light direct and a geom light direct. So here's the environment lights contribution, which is most of it. And then we can go to, here is the geom lights contribution. Wow, how cool is that? So now that plus this equals this, because those are the individual direct light contributions to it. When we render this, our output image can store these as separate parts of the file that you can read. And I'll show you that, how to do that in Houdini's own compositing part. So that's pretty cool. As I said, there's a bunch of other ones that you can do, but this is really the only one we need for right now. And now let's turn on that secondary scattering business that I teased about. So, like I said, when we render, we want high quality settings, and when we're playing around in Houdini, we want low quality settings. So what we can do is basically say, let's make a take, which is a bunch of overrides. These overrides, I'm going to call HQ. So they'll inherit all of the settings. I mean, obviously the main take is what we're usually in. You can see it up here too. Main take is what we're usually in, making all our changes and stuff. And HQ is going to say, let's keep all of those settings, but make a few changes. So we'll render with HQ. So while we're in the main though, which is again, when we're just kind of messing around, let's have the low quality settings be in the main take. So what might that look like? For one, we want our noise level to be higher. We want our stochastic samples to be lower. We'll keep them at 4. And that might honestly be good enough. You could, again, come down to 1 and 1 here to make it even faster. I don't think we need it to be that fast. Right now it's rendering at, 4 seconds. Mostly because we're doing the half resolution. Maybe we can take advantage of going to, where are you? There you go. Here we are back to our full resolution, which obviously takes longer. But we can see more details now, even with the zoomed out kind of thing. So coming back to sampling, maybe we will go down to like 2 stochastic samples. Because again, this is just what we're doing here in our viewport. We will have our HQ one in a second be the other thing. So that's cool. So that's where we were. Here we are now. I'm going to say that's good. Stop this. Now let's go over to our HQ take and let's shop for what we want to change. So in our HQ, we want the noise level to be the default, which is 0.01. Remember, we want our stochastic samples to be 8 when we're rendering. If you think you might change some of these other ones, you could always just preemptively include them here. Just so that they have they're set in this take either way to be the nicer thing. Pixel samples is probably a good candidate for that. So now you can just come back in here and change those things, knowing that in the take list you can see these are the overrides. So whatever's happening down here in the main area doesn't matter. They're going to get overridden with these here. Now, finally, when we render, we'll have it actually say HQ, or we'll just change it to HQ ourselves and then render it when we're ready. But so now we have those settings stored and ready to go for when we need them. So that's pretty much it for takes. Easy, right? I guess I might as well demonstrate it actually working though. So here we are in the main phase, or the main, too much magic cards. Saying main phase. Oh man. So there you go, we're in the main, and then if we take a snapshot, we go to HQ. It's just using those different settings now. And so now if we toggle back and forth, you can obviously see the difference. Just in case you didn't believe me. Cool. But we'll go back to the main. All right, moving on. All right, so we're almost done with the simulation part proper. I just want to throw a few microsolvers in to kind of break up. You know, we still got this like kind of very chunky, blobby look to this that's, you know, not really as good as it should be. So that's what we use our microsolvers for. So make a merge node. This last one here says forces, so that's where I like to put it. First things first, gas disturb, our favorite node. They've changed it a good deal in Houdini 18. It still does the same thing ultimately in the same top level way, where we have a reference scale, which is like roughly the size of the features, where to do it, and how strong to do it. But they changed a lot of it under the hood now, and honestly, it works really great now. You don't need to change that much. Now, it's probably just too strong right now, so it's really tearing it apart. I think it's tearing it apart too much. So I'm going to bring this down by a factor of 10, like so. So now this is nice. So now we don't have the blobs anymore. See, now it's nice and like kind of fuzzy. So that's cool. I mean, that's really enough. We're not going to go so crazy with our sim in this lesson. But that'll still look nice regardless. Let's make a gas turbulence for bigger displacement of like the idle wind currents. Gas disturb is really the little micro currents in the air. It's the interface between the heat and smoke with the idle air doing its little things that it does. But the gas turbulence is more of the macro, bigger things. By default, the settings are kind of quite for small features too, so we need to make the swirl size way bigger. So now you can see how huge and smooth these changes are. And let's make it just not do it that much. I just want a very subtle movement around to just kind of swirl up stuff that's been there floating in the air for a while. And we turned off before the dissipation. So let's just make one now, our own, that's better and cooler. And I'm just gonna have the diffusion just do a little bit. How about we have it do, try at 0.1, see what that does. It might be, it's probably too much. This sim just isn't that long that it really should dissipate that much anyway. So I'm going to say diffuse out a little bit and delete out a little more than that. But I want to keep kind of a lot of the detail. You know, if you make diffusion too high, it just blurs everything together. And you just have a soup. So this is a nice way to do it. Don't be afraid of diffusing things. A lot of times with CG, people are like, oh, but I want to see all the details. And it's like, well, in real life, the smoke diffuses pretty fast. And it does kind of turn into a blah, especially in the older area. So I will try to keep diffusion down for your sake. But, uh-oh, look, we're losing some of the cache. As we're playing, we're losing the cache over there. If you have a lot of RAM, you might as well go to the cache setting here and just increase this. Now I'm dedicating 50 gigs to the cache. It could be nice to just not worry about losing the in-memory cache and just having that be super high. Now I can run this whole sim and it won't run out of thing. Okay, so we added our microsolvers. We may need to tweak it later. This is still a relatively low-res sim. But nonetheless, it's still quite fast. I mean, if we look at this, 200 by 200 by 144 is referring to the theoretical voxels that it would be if every single voxel was being used. It's obviously it's using much less, as we've talked about endlessly, because it's sparse. But it's a good point of comparison anyway. Typically we've said try to get like a 600 by 600 by 600 if you can. So this is a low res no matter how we slice it. But we'll be able to go to higher numbers here than we would normally get to in a dense pyrosim, because so much of it is not really being used, as you'll see. All right, so they're done. We're done with the shape of the smoke. So there's a few little tweaks that we can do now that we have the general idea here set up. One is, because it can only do the pressure and some other various things with how the sparse solver works, there are some little issues with the simulation. Nothing too crazy, but one is this advection reflection. If you look at the little tooltip text, it says attempts to inject energy lost due to pressure projection. It's a nice little thing you can turn on and just feel good about yourself. You don't need to even know what it does, but it is helping. It's actually just trying to, whenever you do fluid sims in general, you're always kind of losing information and velocity between the voxels when things get pushed around. It starts to lose and smear and blur some of the information. This tries to compensate for that a little bit. So just turn that on and, again, give yourself a pat on the back. If you're feeling especially cool, do double project. I like single project because I don't know what the difference is. So there you go. Single projection's cool. Another thing we might want to talk about is the actual bounds of the sim. I mean, it is automatically doing this, but because we're just letting it do it, it could get out of control. Like if it just kept going, like super high into the air. It doesn't really seem like it does. Like we can pretty much see the extents of this. But if you don't know, if you're just running some sim based off of, some wild particle sim that you don't know what it's going to do, you can enforce boundaries. That is on here, on the actual smoke object itself. Center and max size. So what I like to do here is say, let's make a box. Let's draw it out here and say simdims. And we're just going to make a box, essentially, that roughly conforms to our view here. So something like, I'll go into wireframe mode here. So something like that, and then, you know, we'll want it to be, you know, big here too. I don't know. Once again, I'll just clean this up. We'll center it on the X, because why not? The Y might as well just be half of this all the time. So copy the size Y, paste it here, multiply that times 0.5. So now, you know, if I want to make this bigger and smaller here, it will be fine. I'm just going to make this be like, I don't know, is 18 good? Let's just try it. And then this is probably way too deep, because it's a pretty thin sim, as we saw. I'll make it 16. So there you go. We don't want the smoke to reach the top and then hit a wall and then get deleted after that, which is what the sim will do if we're not careful. So we don't want this to be, you know, too low. Like, you can't do this where we're like, oh, but this boundary is at the top of the screen. Well, sure, but the smoke is in the middle of this box. It's going to hit the ceiling here. So we can't do that. So let's just go make it high enough, maybe even 19, just to make sure. So there you go. Now we're absolutely sure that we'll never see it hit the ceiling. So there you go. So copy parameter on the size, jump back into, or I guess we were already there, come back into the sim here, and say turn on max size, paste those values, go back. This could be the kind of thing would benefit from having the 2 columns of parameter network view stuff that I do sometimes in these lessons. Well, I don't think it'll be too necessary in this lesson. And paste the center. So again, we don't see that. We don't see that box here, but it knows. So now when we run the sim, the same thing will happen. I'll press W again to go back out of wireframe. It is stopped up here. So it'll force, if there is simulation happening up here that we don't want to happen. I mean, hey, we could have just had particles that just shoot straight up out of the viewport, and that's exactly what we wanted to do. We only want to see it where it is in view, but we might have particles just shoot quickly up like crazy out of the viewport. And we don't want it to sim up there. So there's still a very good reason to have a maximum size. Okay, and the last thing we want to do is the easiest thing. Literally, remember this, voxel size. So just copy parameter, jump out here, and let's have our voxel size here be in terms of that. There you go. So now we're all set up, ready to go. Huzzah! So let's talk about lights now. You know, we have a light already, which is our distant light here. Well, really, it's a sunlight. We changed it in the thing. To reiterate, there's an idea of area lights in general. So this is a sunlight, but we could have changed it to a grid. This is also an area in a sense. Let's ignore what's going on down there. It's any kind of light that has a surface. It is an entire square. Historically, a lot of lights were just like point lights. It's not really a sphere. It was literally just one point. So when we would do lighting calculations, you know, the ray would come out from the camera, which is over here. So it would shoot out into the scene, and then the lighting calculation would simply say, okay, and I'm definitely going up to here, or at least I'm checking to see what the shadow is, right to here. And it's easy. It's just 1 point. It's very fast, but it's not realistic. Most lights are not an infinitely small point in space. So we've seen a few of these kinds of demos at this point, but just to be clear, so now we only have pretty much just one secondary ray going back, because we don't need to sample that larger light in multiple places. We're going to get these hard shadows like this. There's not ever going to be like an average of these rays, of these secondary rays. It's either going to be blocked or it's not. So point lights are very fast, but not realistic. Commonly used in video games because they are very fast. A disc, though, however, has size. You can change the size. I think you can change it actually on the area light options itself, like so. Make it bigger and smaller. What effectively happens, the bigger the area is the softer the shadows get. The smaller it gets, the more like a point light it becomes. Essentially, the reason why the shadows get softer is, that's the beauty of these area lights. They're wide, and therefore there's greater opportunity to get this averaging, the averaging that leads to soft shadows. See how there's that nice gradation here on each side because of the averaging that's going on. There's a lot of opportunity for rays to, like in a situation like this, about half of them are being blocked. So they're getting averaged together, the dark rays and the light rays. I also have it in here. These don't get light just because they have to travel so far through this fog to get back to the light. So they end up getting occluded just by their own density. Never mind these like geometry things out here like this. But what I want to be clear is, an area light can basically become a point light if it's small enough. There's just not that much opportunity for that averaging to occur. So we end up with sharp shadows, like so. And the opposite is, of course, true as well, where if we were to come back, make the area light crazy big, if it's too big, now it'll pretty much always have a chance. There's never really any spot on this that's completely in the dark. It gets maybe dimmer over here, but as you can see, even right behind this thing, we're still getting, it can still see the light a little bit. So we get something like that. So that's what happens. The larger the area light is, the more opportunities it has to actually be blocked, and the more opportunities it has to actually receive the light. Whereas again, the smaller it gets, it will either hit it or not. And there you go. So you get a sharper shadow. So all that is to say that with the sunlight, which is fairly commonly used, a sunlight has area, but it's also infinitely far away. So the samples that sample it have to be parallel to the sun. So you get a nice looking soft shadow that doesn't feel like it's being cast by something nearby. If this was a point light, especially if the point light was, down here near this, this is going to cast shadows going this direction, and it's going to cast shadows going this direction. So it'll look like there's literally a light bulb in the scene casting like a perspective all over the place. Whereas if it's a sun, it's not actually here. It's this orientation, but it's not actually here. It's just parallel lighting going up out into space, but it still has a soft edge. So sun lights are used. We've been using them already to do this, but I'm going to stop using it. And in fact, I'm going to turn back on our ground plane. Just put the star back in here. Let that go. And that's the last time we're going to see our sunlight being used. Nothing wrong with it, just not going to use it this time. Cool. So I'll do a snapshot again here. Very good. Let us continue with some other lights. All right, so back to this. Whee. So cool. One fun thing that we have now to play with, especially for interactive rendering, is if you crush down all these various settings so that your stuff is super lame looking and grainy, what you can do is turn this button on here if a few things. This is the NVIDIA optics denoiser. Tilt tip text is not turning on right now. I don't know why. But I'm going to turn it on. And let's see what we got. What this does is it takes grainy images and makes a lot of assumptions as to what it probably should look like. And so things will end up looking, see how smeared out this looks right now? So there's no grain. It also looks wrong. But as it continues to refine the image anyway, it'll start looking more and more right. And ultimately, we're at the end of it, we now have an image that doesn't really have much grain. It might be wrong, still in parts, but it does a pretty good job for this interactive rendering to get you to a non-grainy image faster. So if I looked at like the geometry light indirect, or rather, because I'm not using the indirect right now. Well, anyway, yeah, it smooths things out. It uses AI, honestly, fed off of billions of images of what the grainy version looked like and what the non-grainy version looked like, and sees the difference. And so it does a pretty good job of smoothing things out. Or, I mean, it does a good enough job. So there is that version of it, and if we turn it off again, you'll see, obviously, the regular version. Now, it can be too aggressive. It might smooth out actual detail that you want. This is really just for the interactive view. This isn't really for your final renders. So obviously, there you go. But you can see how it really did smooth out all this grain. So in areas like this, you might have just been like, yeah, that's what it looks like. Maybe it is, again, more obviously wrong in areas like that. But that's because we gave it these insanely bright lights that it's probably not used to. It's AI, it's not perfect. But it is good enough to remove quite a bit of the grain, as you can see. Most of the image looks pretty good. So it's a nice way to, when you are crushing all of these settings here to make you have horrible images, to have it actually still look pretty good. Imagine we did a 1x1 render like this, but if I turn on the optics denoiser, it still smoothed it out. It doesn't look that good, but that's because we really gave it trash input to work with. So it's still pretty impressive stuff. I should have said up front, and I'll put an annotation now, you may not be able to use this. For one, you have to have an NVIDIA card. So Radeon, not going to work. For two, you have to have an NVIDIA card that's new enough. I believe it has to be approximately a card since 2012 or so with a Kepler architecture. Number three, the card has to just be good enough in general, or else it'll, might take too long. But the main thing is you need to have a Kepler-enabled NVIDIA card, and you need to actually download it. It doesn't come with Houdini. It's built in and ready to go, but you need to actually go click render and go download NVIDIA Optics Denoiser, and then that'll bring you to a website, and you can download it, and then it'll work. So God knows, that's one of those things that'll probably change in the next version or something, but enjoy it while it's there or whatever. Hopefully someday there's like a denoiser that doesn't require you to have an NVIDIA card. But yeah, pretty fun to work with that. I think it's super nice to iterate faster. If you are an insane person, and I know some of you are, and you wanted to use it for your final images, you can. If you go to the images, the extra image planes thing, or actually not even extra image planes, if you just go to output, the default Gaussian pixel filter is this slight little blur that's applied to your image. You can choose NVIDIA Optics Denoiser from this, and your final images will actually now use this instead. It will work. The issue with it is that it doesn't know. The AI is looking at, it's saying, based on all of these various still images that I've seen before, this is how it should be denoised. So in addition to it just having problems anyway, it doesn't know anything about time. So its solution here might look different enough on the next frame that you will notice. So things might jump around and turn on and off and flicker in a weird way from frame to frame. And in fact, it's likely that they will. The more specific and non-noisy image you can give it, the less it will do that, but then also the less of the point of using it in the first place. So it is not, as we say, temporally cohesive, meaning it's not consistent through time. So it's still great to use if you're making a single image, then by all means. But used for an animation, it can and will have issues, and especially if it is a noisy image, which is why you're using it in the first place, it will be even more likely to look different from frame to frame. So just so you know, you can use it. It's very fun, but probably don't. All right, so we're almost ready to finish up here. I'm going to say let's make a file cache to actually save these volumes. So say file cache sim, something like that. I'm going to say go to job here. I'm going to put it in my sim folder and say it's going to be $OS, which is the name of our node, which is file cache sim. That version 0, the current frame number, and then bgo.sc is the file format for geometry. So there you go. If you middle click it, you'll see the full thing there, including the frame number. So that's cool. It's 1 to 120, which we already know is right. What we might want to do though is realize we're getting the temperature field because we asked for it here. We're not going to use the temperature field to actually render with. You would use the temperature field if you're doing an explosion, because that would dictate the color of the fire. But we're not doing that here. Let's not import it. Let's not save it to disk. These files are going to be big enough as it is. No point of doing that. We don't have a rest field, so don't even worry about that. The velocity field is trickier This sim isn't moving that fast that the velocity blur will really matter that much. It might matter right at the source, but it's going to slow our sim down quite a bit. If you have a lower grade computer, I would say turn this off, both because it's going to take up a lot of disk space because it's a vector, meaning it's 3 times as much data as the density field is, which is only one dimensional. If you're not sure and you have the disk space to kill, then yes, just save it. Otherwise, there you go. I'm gonna do a cache right now of this, and we're gonna look at it. Should actually probably run pretty fast. But the actual sim we're gonna run is gonna be higher res than that, and for that we might walk away and let it do its thing. So anyway, here it goes. We'll take a look at it in a minute. Okay, so click load from disk. We scrub through it. There we go. We got our whole sim there now. I guess technically this volume visualization should be after this so that we can make changes to it if we needed to from the cache, but either way. So there you go. Let's just run a little flipbook. I mean, again, this is fairly low res, but let's just get an idea of it. Let's make sure that like things aren't getting chopped off unexpectedly somewhere. The color all works, everything works. It seems like it's going to be good. Yeah, so there you go. That looks nice. Good enough for me to say let's up res this and then actually let that run. This is also a good time to say let's look at how big those files are. Oh, that was a mistake. Probably don't want to store these in your actual documents area. Usually a good idea to put this into some like data drive area. So a good thing we caught that before we did the higher res thing. Apply to Houdini temp is where I'm going to do it. I'm going to make a new folder and call it, volume 3, version 2 temp. So we'll put it in here instead. And then that'll be, I'll just copy this here. And then that'll be that. So I'll just save it to disk again real quick because it's still a cache in memory because we increased the cache from before. So it's not even resimming it, it's just rewriting it. So there you go. So these files are here. They're not that big. They're only like 100 megs at the most. But of course, every time we increase the resolution, or rather, reduce the voxel size by half, everything is going to be doubled along each axis. So twice as many voxels on the x-axis, twice as many voxels on the y-axis, and twice as many in the z. 2 times 2 times 2 is 8. 8 times as large. These things will become, this is going to go from being 115 megabytes to a gigabyte per frame. So just keep that in mind. Then that's if I went to 0.05, which is, again, reducing it by half is going to double it along every axis. I'm going to go ahead and say, go even farther, 0.04. It's going to make these files fairly large. So these files are probably going to be probably about 1.2 gigs per frame by the end of it. But, you can buy terabyte drives now for $100, so, or less at this point. It is well worth it to have that data there. Although, just because you can doesn't mean you should either. With a very high quality volume means you will need more steps in the rendering process as the rays penetrate the volume to render them, as we'll talk about. It will make it slower to render also. So it'll be slower to sim, and it'll be slower to render as well. So keep that in mind. Like this sim is actually going to be quite fast, even at this size. Even with a gigabyte cache file, you'd think that would take a long time to sim, but it's actually not because of how fast the Pyro sparse solver is. So, but it will still take a long time to render. So just don't make, you could set to 0.02 and have 10 gigabyte cache files, and maybe you do have enough disk space for that, but they're going to be very slow to render. And they're going to look good like this anyway. So just saying, don't do it just because you can. Okay, so I'm going to save this to disk, and this will probably take still a surprisingly short amount of time, but yeah, it'll take a few minutes. So I'll see you in a minute. So there you go. Yeah, you know, kind of looks the same in preview mode, but trust me, there's way more resolution there now. It kind of gets blurrier by the end because the viewport volume preview is just saying like, hey, I only want to show like 100 voxels maybe from left to right. And so when you have less to show, it looks more high res, but by the end, it's spreading that out over the whole thing. So in case you're wondering why it's so blurry, it's going to be way higher res when we actually sim it. But anyway, it's there. It worked. It's cool. We can middle click and hold on this, like let's say on like the last frame, and say, oh wow, look at that. It's 131 million voxels now. 750 by 500 by 300. So we're kind of in the sweet spot that we want. I'm always in my head. I'm always trying to get to like 100 to 150 million voxels. You can certainly go higher. I mean, my computer simmed this. I mean, sure, again, it got to 1.2 gigs by the end, but it went from 1218 to 1227. I mean, it's incredible. 9 minutes to get to this incredible amount of voxelage. So yeah, if you went down to 0.02 voxel size, you could have, you know, it might take 8 times as long, but 8 times as long as, you know, 9 minutes, that's fine, an hour, right? Who cares? But then you'll have 10 gigabyte files and your actual render will be slow. As we'll see when we render this, we're gonna have enough detail in this that we probably don't need to do that. But you could. So anyway, so let's actually talk about what we're here to do, which is we wanna render stuff. We wanna start setting up for our render anyway. We never wanna render our, you know, little helper node here. We wanna make some, what I like to call render nodes themselves. So say render smoke, and that will just be an object merge that grabs, actually I don't know if I made a null over here. I did not. Keep in mind again, the volume visualization node will have no actual bearing on what it actually renders. This is just for the viewport. So we're gonna get that node, and there it is. So when we render, when we tell the mantra or whatever renderer you end up using to render nodes, we're going to render this node, not this node. Let's also set up a ground plane or ground whatever. Ground! Make that green. So I'm going to literally put a grid down. Let's actually get our smoke back. I'm going to say make it wider and make it maybe the same. 50, 50, 50 might be good. It's probably fine. Let's make it into a NURBS so that it's smooth. And I like to just grab this, bring it up. You can see because it's NURBS, it does the bending like so. Looks like we got to go a little bit higher, and it looks like we have to make it a little bit wider. But there you go. So now we have a ground plane and background that we can use. Now we're also going to talk about compositing this lesson. So oftentimes what we do in Apply Houdini is we just kind of render everything at once. In practice, you usually render the elements individually, and sometimes even the elements, as we will do, will break down into the different lighting contributions, as we'll see. So just so you know, we will do our preview rendering with all of this at once, but we will actually, in this lesson, for once, render things out separately so you can see how to composite them together. So object merge again. Let's go grab our ground plane, like so. Now we have it, like so. And there we go. We got some render nodes. What else we gotta do? We gotta actually make a mantra node. Now this lesson, we're gonna talk about mantra, because that's the time that we're living in. Mantra is still a great renderer. It's not the fastest renderer in the world. Karma is coming, and will be GPU enabled and stuff, and we'll all love that when that is up and running. But right now, it's January in 2020. Mantra still reigns supreme in Houdini anyway. You might use Redshift. That's fine too. I don't know that much about that. Mantra is... The only problem Mantra has is that it's slower. Otherwise, it's superior in pretty much every other way. So if you have the time, you might as well use it. Also, it comes with Houdini, so even more reason to use it. So, Mantra Smoke. So there it is. It still works great. Some initial settings we'll do is we want to have the frame range, obviously be it. The camera is already set up. We want to use physically based rendering, which is just changes how the lighting works just a little bit, mostly under the hood. Let us override the camera resolution to half resolution for now for our tests, just so it doesn't take as long. And I'll say our distant light that we made before, oops, come back. Let's turn it into something a little bit fancier, which will be a sun. A sun is also a distant light, as the sun is very far away, but it will have softer shadows. I'll explain how those lights work in the lighting chapter. But for now, I just want a light that we can demonstrate some of our settings with. So cool. Save that. And the last thing we'll do is let's just see what we have so far. Oh, actually, we didn't tell the mantra node to use the render nodes. So to delete the star in the candidate objects, we don't want it to render whatever just happens to be on. We want to only render things that have R and DR in the name, which, as you recall, are the two things we just made. So let's see what this looks like. And then in the next chapter, we're going to look at materials to start setting things up so that we can then look at our lights and things. Great. So the first stop on the learning train is going to be the sparse solver. And sparse solver is good at simulating stuff that's not just like one big blob, but stuff that's happening all over the place. So we're going to make a particle sim to shoot smoke trails in random directions. And that means that we're going to need a particle sim. So drop a geometry node down, call it the sim, jump in. Now obviously there's a particle series for Applied Houdini. Even the first lesson is free and would tell you more than you need to know with regards to how much we're going to do particles here. So I'm going to try not to dwell on particles too much. I am going to go through it quickly. So just make a sphere to be our source. We're going to shoot particles out of the, like in the normal direction of the sphere. Let's do a clip. We don't want to shoot them down. The clip is centered at the origin, conveniently. So we're just going to have this hemisphere here. I increased the frequency on it also to 8, just so it's smoother. We could also make it just a lot smaller. I just want this to be, again, just a little source to shoot particles out of. Nothing too crazy. Now you'll know, perhaps, from the particle series, or not, make a pop network. It's really just a DOP network. Dynamics operators. The same thing that Pyro uses, the same thing that rigids use. Back in the day, pops used to be their own area particle operators. Now they just live in dynamics. So by default, this is using the first context geometry, which is this first input here. So by default, if we space G to look at it, we can see particles showing up on the surface. They have no velocity, so they just sit there. Let's say we don't want this many. If you go to the birth, it's making 5,000 of them per second. We want 2 of them per second, I think. That seems much more reasonable. So now, if we turn the guide off, you can see we're just making a few. And my computer is so incredibly fast that it can handle a 10 particle sim even faster than 24 frames a second. So that's why it's playing through these 120 frames so fast. So if your computer is also so powerful that you can handle 10 particles, click on this clock. The clock will force the computer to slow down to 24 frames per second, just so we can get a better idea of what this is going to look like. So come back out here. We need these to shoot up into the sky and come back down again. So we need to do a few things. Let's actually do gravity first. We need the come back down again. And while we're thinking about coming back down again, let's do a ground plane to collide with. So ground plane, merge into the gravity thing here. Oh, like so. The merge by default is a collision where the left affects the right, so the ground plane affects the particles. I'm going to turn the display off on it. And the particles themselves are just kind of stuck here now. Let's shoot them into the sky. So go back to the attributes that we were starting to do and say, let's set the velocity. Let's shoot it up. So the initial velocity is, then the y direction is 10 plus or minus 1. So we can see, like that, they're coming up and they're coming down again. Let's make it go up higher. Cool. Let's make it go wider. So we'll have the variance, because remember this is the plus or minus. We want it to be up to 10 in the x direction or minus 10. So now we got something like that. Let's give it some depth in the z direction, not too much, because I want to keep the actual simulation kind of scrunched together in that plane, if possible. This plane, I mean. That'll save us some simulation time and such. So that's not bad. And then we'll just vary up literally the up direction. So it's 15 plus or minus 5, and so on. So there we go. We also don't want them to live forever. So go to life expectancy, say you will live 2 seconds, not 2 frames, but 2 seconds, plus or minus 1 second. So of course that is 1 to 3 seconds. That will be randomly assigned. And we will use that later on because these are going to be where our smoke is sourced from. We're going to use that later to say, how far along are you into your life expectancy? Like, what is your age now divided by the maximum life? That's how far along you are. We'll use that to drive the size of the emission, and we'll have it taper off. Cool. So that's going well. Back out here, we need to not... Right now we're importing the ground plane in addition to the particles, because the ground plane, rather if you look down here, middle click and hold, ground plane is a dynamics object, and the whole pop object that stores all the points in it is 1, 2. And this is saying get everything. So I'm just going to put star pop star, which means get me all objects that have pop in the name. It's only this one. I could literally just type pop object out, but I'd rather be lazy and just type star pop star and then invest all that time I saved in explaining endlessly why I did that. So there you go. We now have these points. And last thing we're going to do here is we'll make a wrangler That's right, we're going to use some Wranglers, we're going to use some Vex in this lesson, just a little bit. Don't worry. So I'm going to make an attribute called density, because it's just an at without anything in front of it. It's just a float, meaning it's just a decimal number, a regular old number. Make it 1.0. That's it. We're going to use that attribute to convert that into smoke in a minute, or volume I should just say. And let's finish off this chapter with a null that just says, these are the points. Behold them. Very good. We are going to use is an environment light. We've used these lights, we've actually used the sunlight too in our previous lessons. We just never really talked about how they worked. So here's an environment light. And what I want now is I want this distant light still to be here because I want to see these shadows and things in their viewport, but I don't actually want it to be used by mantra. So I'm going to say, let's look at our mantra node and say, don't just use any light. Well, rather, use any light, but do not use that light. So let's see what that looks like. So now we're going to use our environment light. So the environment light is a harder light to render. It's harder because it's everywhere. It's a huge area light, in effect. It's like a dome, essentially, that has a texture on it, or maybe not. It just depends on how you have it set up. But right now, it's just a white light that's coming from all directions. So let's come back in here. It's super grainy. Let's go to the environment map and say HFS / which is Houdini file system. Find these HDRI images. We're going to use the Skylit Garage this time. The Skylit Garage is an environment map that we can actually just look at out here. It looks like this. It is literally a skylit thing where it's very bright above us. It's an image. This image, when it's sampled in the same way, where rays come out from the camera, they hit the thing, and then we send rays in all these different sampling directions. Some of them will find the brightness above, some of them will find the dark areas over there, and they'll be averaged out. But as you can imagine, most of the samples towards the top of this thing are going to find the bright areas on top. So it ends up looking like this, where we went from this, which had a kind of a flat light coming from one direction. Now we have this kind of more dynamic light coming from lots of different directions. To help the renderer, we can say clip to positive Y hemisphere, meaning don't ever even try to find the image below ground. I mean, there is an image below ground, but we're pretending that there's just a ground everywhere here. So don't even bother trying to do that. So that can help things a little bit. A lot of times the environment lights, we want to make them brighter. So there you go. It's looking way more interesting. Environment lights are very interesting because different colors and brightnesses are coming from different angles, just like in real life. In real life, things aren't just universally white, or it's not just a powerful light coming from one angle. Now we've gone from this to this. It's a pretty big improvement. You can use both lights at the same time. You could still have one bright light as like a key light coming from one angle, but in any case, this just feels way nicer in general. So we can see it looks nice. It's grainy and stuff right now because we're using those quality settings. Take a picture. Let's see what it looks like with the HQ settings. See if some of that graininess goes away. Because if it doesn't, you might need to increase the sampling quality on the light itself. Similarly to the Mantra rendering quality stuff here, where we don't want to just increase the pixel samples and say everything's quality goes up everywhere, every setting is going up, essentially. What the lighting thing does is saying, hey, I know the environment light is hard to render. There's different shadows and brightnesses coming from different directions. Maybe it needs more samples to resolve itself. So you might increase the sampling quality just on this light, leave other lights alone that are simpler and don't need their qualities increased. But you can see how much longer this is taking to render now. I mean, it just looks better though, but it is taking longer. Perhaps while we are in our interactive mode here, I'm going to go back to the main interactive mode. I'm going to say, let's go back to doing the override camera resolution thing. So we're only rendering half as much, or really a fourth of as much. So there you go. So now we can compare this to this. Cool. So it's looking nice. Obviously, you can use different textures on the environment light itself if you want. This is just some of the ones that come with Houdini. Lots of websites are more than happy to have you download some cool ones for a price, or you can go out and take your own. You have to like sew them together into like a spherical image, but there's plenty of software that will help you do that. In production shots, working on movies and things, you will often be given those environment spheres. They'll be taken at the set itself, wherever the actual filmed action is taking place that you're, integrating your own visual effects into. Hopefully there are, the visual effects supervisor who was there at the set thought to take those pictures so that your effects can live in that lighting itself. Even if the specific shot doesn't have its own sphere, usually just like, a general setting, like this is the desert environment sphere, or this is the city street environment sphere. So things like that. So this is looking quite nice. I think you'll agree. Take this little screenshot. These are going to be all over the place. The HQ probably, actually, we need to make sure that when we render the HQ take later, that we are not doing half resolution. So we need to include this one and turn that off. That would be a bummer to set a render off overnight and then realize that it was just half resolution. All right, so that's that. Last thing is to talk about geometry lights. All right, so we're going to talk about geometry lights. First thing I want to do, though, is maybe kill some of these oversized images. That way I can make a nice... Yeah, look at that. Love doing that. Best part of my day. So, geometry lights. Geometry lights are what they sound like. They are bits of geometry. They're treated like lights. That sounds like it would be expensive and terrible, but it doesn't have to be. Also, now we're talking about this environment light. I'm going to turn off enable light in viewport. I don't want to see that. Okay, anyway, so when we were talking about our distant lights and things like this, you know, like the grid or disk, things all commonly referred to as area lights, they are essentially geometry. This is a square. The disk is a circle, you know. So these are geometry. They're just kind of easy, fast, simple, straightforward, commonly used geometry. But if we wanted to have arbitrary geometry, we can do that too. What I want to do now is have the things that are emitting smoke, I want those to be lights. Yeah, that'd be cool. Just little burning tips. We have the particle positions, so let's put little spheres on those particles and say these are lights, meaning when you do the ray trace lighting calculations, try to find those spheres and see if you are illuminated by them. So it's pretty straightforward, actually. Let's make a bit of geometry over here, and I'll call this geom light. I'll call this light spheres. So light spheres, not something that'll be rendered explicitly, but we're just setting up the geometry that the light is going to use. So what do we need? We need the points all the way back from our particle sim. So that was back in the sim points. And there they are. And we want to put a sphere on them. So we can use copy 2 points. It's pretty important here that we keep it as the primitive sphere, not a polygon. When it's polygons, now it's like it's 80 polygons and 42 points times all these things. Now it's hundreds of polygons and points. We don't need to do that. If it's just a primitive sphere, it is just the spheres. It is a point and a radius, and that's it. It's very easy to represent a sphere in computer graphics because, again, it's just a point and a radius. Doing intersections, ray tracing intersections against a sphere is very, very fast. So even though this is arbitrary geometry, and in many ways it's kind of a weird light source, it actually still doesn't have to be that expensive. These are too big. So if I were to have, let's bring our smoke back on so we can see. Because we need these lights to, you know, live in the smoke. So make them half as big. It's probably still too big. Make them 0.25. So they're inside of that. Very good. And that's it. That's all we had to do. That is our geometry. Now to actually, so make a copy this, turn that off. Just drop down a light. And we'll call this geom light 1. And to set it up, we change the type from point to geometry. We go to area light, because again, it does have surface area. Turn off normalized light intensity area. What this would mean is the more area there is, the less bright any given part of it is. We don't want that. We want, if there are more lights, we want them to be brighter. So turn that off. Turn off self-shadowing. It shouldn't block itself. It's just a glowing orb. You can override the material if you want. We don't need to. And the geometry object itself is that, the thing that we just made. Now, unfortunately, when it tries to show you the light in the viewport, you know, it just puts it at the origin. It just puts it at wherever this thing actually lives. But it's not real. It's not going to illuminate this in the viewport, much in the same way that the environment light doesn't do anything in the viewport, whether it's on or off. The distant light does, as you know, it makes the shadows, which we like. But this is another light that doesn't really work in the viewport. It would be too complicated. So that's about it. Let's see what that looks like. Go back to the render view, render it. We're back in our main thing here, so it should be pretty fast once it loads it all up. And we can kind of maybe see something. I'm not sure if I do see it. It's probably just not bright enough. So just increase these things by powers of 10 until they work, and there you go. We can see them. So there you go. So it's still not that, it didn't take that long. Let's go back to the same frame we've been using, so 113. But yeah, using spheres are pretty fast. So it's like light instancing. It's like we're instancing these lights, but we don't actually have to like figure out how to actually instance lights. Just putting actual geometry spheres in the scene and saying you are lights is often enough, as we can see. So that's pretty rad. This is another kind of light where, because it is an area kind of light, sometimes it can contribute graininess to the scene, so you might need to increase the sampling quality to 2. It shouldn't make it take that much longer, but it can improve the look of the graininess quite a bit. I also think this could probably be a lot brighter. So it's very bright now, and this one actually also has a little bit of brightness. So that's cool. We went from this to this. You can see the light trickling through the smoke as well. So it's nice. Whee! So that's it. That's it for the geometry light. I mean, you can use any kind of geometry for that. But, like I said 100 times already, spheres. Cool. All right, so the simulation finished. Turns out, though, that there is a bug in the sparse pyrosolver, at least as of the time of this recording. And speaking of the time of this recording, I'm actually recording this after I finished the lesson. I had somebody write into me pointing out this problem, and they're totally right, and it's totally missing from the pyrosolver, and I'm totally going to tell you what that thing is in a minute. But I also just want to say, first of all, that we're going to fix it now. It's a really easy fix. It will be rolled into Houdini soon, and at that point I will remove this chapter from the lesson. But all this is to say that the rest of the lesson, I did not have the benefit of this fix, so my renders are going to look pretty good, but they won't look as good as yours will now, because you're going to actually have it working correctly. And what am I talking about? Well, on a black background, we actually don't see the issue, or at least not much. But if we, let's say, chose a frame, tap back here, press D to go into our viewport and go to light, we can see there's like a dark edge around everything. And sometimes the dark even like bleeds in further. So that's not good. In fact, I have a second little view thing here where you can see it kind of develop in action. Like earlier on, it's nice and light around the edges because it's a thin volume. It shouldn't be dark. So this is, you might be tempted to think this is just a viewport problem. This is an actual problem. What's happening is the color volumes that colorize the density of the smoke are not at full color along the edges. If you have any compositing experience, you might be familiar with images that have pre-multiplied colors, and then if you multiply them again by their alpha, they become darker, and that's what this is essentially. To reiterate, we want the color volume to extend beyond the density. It will only be rendered wherever there is density, but we need it to sample the color at those edges and have it be the full color and not some fading off color. So the solver is supposed to take care of that for us. It's supposed to extend the color beyond the edges here and make sure that there is color there and that we don't get these issues. If you still don't believe me, right now we have the shadows on. If we turn shadows off, we can still see this dark area. Earlier on, it is pure. This problem hasn't fully manifested yet. But as the simulation goes on, it gets worse. And again, it looks interesting in its own way, but there shouldn't ever be dark color. All we've ever done is introduced pure color into this. We never introduced dark, edges and stuff like that. We should only be getting that from our shadows. So that's a general description of what's wrong. I understand that it will be fixed soon in the Pyrosparse solver, but for now, we can actually fix it ourselves. And it's pretty easy, and it's actually kind of fun. It's fun because it means that we get to mess around with the granular nature of DOPs. In particular, this used to work. It worked in the regular Pyrosolver. Now, the regular Pyrosolver is actually a bunch of microsolvers that do various things, mostly combustion related. But this depends on what we're looking at. Some extra stuff. But it all ends up feeding into the lower level smoke solver, which is for all intents and purposes the Pyrosolver. But at a deeper level, the main mechanics of the simulation, the fluid sims, is it being done in the smoke solver. The reason why I tell you that is drop a smoke solver down. That's the inner one that we want. All right, right click and hold it, go to allow editing of contents. Now you can see this little lock that's usually closed here is now open. That means we can go inside and mess stuff up, and we're going to. For now, at the time of this recording, color operations is this entire box up here. We're not going to get into the specifics of what it's doing, but it is essentially taking care of the various color things that it needs to do to make sure that those black lines, those black edges don't happen. So all we really need to do is delete everything else. So this box we want, again, the color one, so delete everything else, like so. Now a few nodes will be left behind. They're just like the inputs and stuff like that. They don't matter. All you need to do is click this orange thing. Right now, one of your other nodes will have it. I guess apparently that. But you click this here, which is the export flag. That means this is now the output of the overall node. And this is the functionality that we want to reuse. So come back out here, and now we can just hook this up into here. So find the advection input. It's throwing an error only because it thinks this is the actual smoke solver and that it needs an actual DOP object to solve. It doesn't actually need one. In fact, the sim will run just fine with it throwing that error. But if you want to, just for completeness, just point your smoke solver into it. It doesn't really matter. Now the error goes away at least. That's it. We've now modified, we've grafted on a piece of the old Pyrosolver onto the newer sparse Pyrosolver. And that's a totally valid and legitimate thing to do, because the context on the inside is a dynamics context, and the context on the outside is a dynamics context. The inside is just a bunch of microsolvers, as you can see, and that's what these are. There's no difference that the microsolvers happen to be inside of a node, because their result is this. So it's a lot of explanation for something that's going to be taken out of this lesson eventually. But let's just take a look. I'm going to run out. Well, I'm going to save the new version of this now that we have that, and now we'll take a look at the result. All right, it's all done, and we can see it just feels a lot brighter now. The colors are more pure. They're not artificially being weirded up by the darkness creeping around the sides. Same thing if we go into the non-shadowed mode here, you can see it's just the pure colors. Yeah. So to reiterate, I am going to re-render all this just for the preview for the class and for the final result to look at and stuff. But yeah, for the rest of the lesson, which I've already recorded and that you're already watching, the volumes will look a little darker because they were using the bugged version. Yeah, that's pretty much it. So onward with the lesson. All right, so one more time for posterity. Yeah. Oh, and then there's the denoised one at the end. I mean, hey, it is denoised. You gotta hand it to him. Very cool. But we don't want to actually send to the compositor, in our case us, this entire thing, the background and the smoke as one thing. Now, yes, we have broken it down into the components, which is great, but we don't want to actually also send the background with it. If I send, let's say, the environment light direct, literally the background is here. So if I'm the compositor and I'm trying to make the smoke brighter, well, it's making the background brighter too. So I know a lot of times in Apply Houdini we do render them all at once because we're not usually focused on the rendering, but this is a rendering lesson, so we are definitely focused on it this time. So what we want to do is we want to have a renderer just for the smoke and one just for the background. So go to that, let's take our smoke thing, duplicate it, and this one will be, we'll call it BG for background. So the smoke will just be smoke. However, it can't just be the smoke because this ground thing still plays a role in the lighting of this. Like the environment sphere is back here trying to shine light this direction, but it can't because this is in the way. So we need to say forced phantom the ground. Forced phantom says this is not in the scene, but it is being considered by various secondary shadow rays. So it'll still be considered in lighting calculations. It just won't be considered for primary lighting calculations. Primary meaning the ones that you actually see. But again, for shadows and all that jazz, it will be considered. So smoke and ground. The force matte is similar, where it will also be considered and you won't see it. But force matte will make it also kind of subtract itself out. So if I had like a sphere in front of this, it would do a holdout of itself. So it would just be like a black area that you could then just add it on top of it later in rendering. We're not going to do that this time, so I'm just going to stick to force phantom. But as you get more into down the road, we're going to do some straightforward compositing. We're not doing that this time. So just going to keep it in force phantom, which is usually what you want anyway. So very good. And then the background is kind of just the opposite. We want to render the ground, and we want the smoke to be around because that's what's casting shadows onto the ground. The light, this is blocking some of the light, so some of the shadows show up on the ground. If we just rendered the ground without this, the ground would just be like, I'm doing great all the time. I've got perfect lighting. And really, that's not true. It should be getting shadows, as you can see. Ugh, I don't like seeing this denoised one anymore. So there you go. So we have one doing it one way, one doing it the other way. Yeah, pretty much that's it. So we can chain these together. You can have them honestly side by side. For completeness, we should have a fetch sim here, what that will do is we can point to back under the sim geometry node, there was the file cache, and there inside of it is a render node, the one that actually, when we say in here, I'm going to turn off resimulate for now just in case. But this, when we click the render save to disk node here, it is actually running this ROP geometry output node, which is the thing that's actually writing the files to disk. So this is saying, by clicking this button, it's essentially clicking that button for us. So we can make a thing like this that says, let's say we made changes to our simulation, and we wanted it to both simulate it and we then rendered it after that. We now made a dependency that says that, hey, you want to render the smoke? Well, first you got to run this sim. Now, I don't actually plan on rerunning the sim, so I'm going to disable it. But I did want to show you that for completeness, that's how we can run the sim and then run a render all at once. Or at least if we merge these together and run our sim from this, do node by node, and then if we ran it, which I'm not going to do quite yet, it would do this first. If you had a render farm, it could do this on one or many other computers and do this at the same time because they don't depend on each other. Not once the cache files exist, these can run separately. So anyway, so these will write files somewhere. Apparently I have them writing here. I'm going to say go to the job, render, and then we'll call this whatever this node's name is, dot version 0, dot frame number, dot exr, which is the standard. And I'm just going to use the same actually for both here. Because, oops, that's not right. I apparently didn't copy it. There we go. So this will resolve differently. This is going to be called Mantra Smoke. This one's going to be called Mantra BG, because that's what the nodes are called. So we're going to render images of just the ground with the shadows. We're going to render images of just the smoke with all the per lighting component stuff, which this will also have. And then we're going to write to two different sets of file sequences. Let's have them both use the HQ. You can either set HQ directly on the node here, or you can keep it set to current and just choose HQ from here instead. There's slight differences to that. If you do set these to HQ here, it will use the HQ settings here, because all it knows is it's using that mantra node and that it uses that take. So you wouldn't get the low quality main settings anymore, because this would be saying to use the high quality ones. So what you might want to do is keep it current and just do the HQ here and then do it. I know I'm not gonna do much more iteration on this, so I don't suppose it really matters what the difference is. But yeah, just remember that if you do set the HQ here, that it's gonna make the HQ happen in the thing there. All right, so that's the general setup. I want to show you one more thing in case you ever are going to composite stuff like this onto a live action footage, and then we're not going to do it. I'm just going to show you how to do it, and then we're going to render this and come back tomorrow, whatever. Background image, there really isn't much else to it. We already know, you might be able to guess what we're supposed to do. And that is, well, read it in, first of all. So let's go find it. There it is, background. If we look at that, it is the background as we know. And then we need to use a layer. This time we're not adding it to it. So the background image, when we're doing compositions that involve something literally layering on top of something else, the lowest image comes first, and then the subsequent higher images come after that. In this case, it didn't matter, because we're just adding them together. Any numbers added together, it doesn't matter what order they are. But in this case, we're not going to use an add. We're going to use the default, which is an over. An over looks at the alpha this time. The over says, well, start with the first image, and then the next image, add it to that based on where the alpha is. Obviously, we didn't add a lot of. Well, I can just show you. If we did say add, it's actually a little bit brighter because now we're not adding it based on the nuance of the alpha, where it's thinner in some areas and denser in others. It should be darker in these areas where the alpha is lighter. And if for an interesting little thing to see just why we had to bring the alpha back in, if we didn't copy the alpha in, this is what it looks like. That maybe doesn't seem that different, but it is quite different. Look how dark it is around the edges. It's almost like it's outlined with darkness. This would be like a easy mistake to make if you didn't realize that the alpha was wrong. What's happening is, if we look at the alpha before we copy it over, again, everything's super bright, but the alpha is extending further out from the edge. And it's extending further out into the black area because there's just black surrounding this. So some of the alpha is now bringing over that blackness into our final image. So again, this is all compositing stuff, but this should be enough to get you by. So once again, we can modify now the background separately, and that's the beauty of this. If you decided, I want to friggin' have a green background, you don't need to re-render your like day-long render anymore. Now you can just drop a color correct down right here and say, you know what? Green. That's what my artistic vision is. Green background, you know, or not. I'm just going to say, let's just bring the gamma down on it. The darker it is back there, the more this whole thing will probably pop anyway. So we still see the shadows and such. That's nice. We could even break this out and have only the environment light be down and keep. I mean, let's just do it. Because I'm talking about it anyway. So just grab well, I'm sure we'll get in trouble doing that. So just grab a channel copy and say target the color. We want the environment light direct. This is the one that we're going to actually turn down. But so we also need the geom light direct, which is just these little bits of brightness. Maybe we want to bring those up. Color correct. Like so. And then again, layer these back together again. We don't have to worry about the alpha this time because the alpha for this is just solid. You know, it's just the entire back. There is no nuanced alpha here. So now I can just say, if I found an image where there is, let's say, so like here's a frame 3, where we do see the geom light contribution. So now I can say just bring down the environment light, but not the geom light. And there you go. Well, I can't really see it anyway, but that's the idea. Real quick, while I have you here, we might have been able to accomplish a similar thing without splitting it out here. Because again, there are lots of other color operations. I don't know why this isn't working very well. You see that happening, right? Anyway, there's lots of stuff in here. Color replace, color correct, change things based on a curve. The one I want to talk about real quick is levels. I like to use levels a lot. And I should also say, just like how we were talking about mantra being like, here's the render we're using now, but maybe you might use other renderers now or later, but the concepts apply. It's the same thing here. I mentioned Nuke. All of these nodes are in Nuke with different names. Like, seriously, this is called the merge node in Nuke. This is called the grade, these are called the grade nodes in Nuke. This is the read node in Nuke. And this is the shuffle copy node in Nuke. So it's all the same stuff. It's just, you know, how fast is the program? How about the rest of its pipeline support stuff? They're all fairly similar. Anyway, we can use levels here to say, hey, maybe make the darker colors even darker, but retain the colors up here. We can also do it similarly with the outputs here. So what this is saying is any brightness lower than this number becomes this number, which is 0. So this is saying the darker colors, we call this crushing the blacks, meaning crushing the black values of here. That would be a way to do it in a nice, smooth, kind of intuitive way. This would be anything brighter than this number becomes this number. So this is basically bringing out the white values here. I'm going to stick with our color correct mode here this time, but explore all the different things that you can do in there. And yeah, so that's pretty much it. Maybe I brought this down a little too much. I'm going to bring it up a smidge. Yeah. Very good. So you can see, finally, we went from this to this. It's brighter. It has a background. We might even say that we did. Did we do anything here? I forget. Oh yeah, we did. So we brought up the actual shininess of the geometry lights. So very good. That's it. So to actually write these out now is we just need to do a where are you? ROP file output, and just it's 1 to 120. Let's just put it somewhere. I'm gonna make a comp folder. I guess there already is one, and we'll call it whatever this node is called, version 0, current frame, and I'm gonna put it back into the EXR format. Oh, that's VO. There we go. And we'll just call this ROP final image. Very good. And this won't take very long at all. I mean, it basically takes as long as it takes to scrub here. So I'll see you in a minute. I'm just gonna run this and then we'll review it and then we'll be done. All right, so there you go. Not bad for having set up nothing really, except for one light. You know, it's very thin and other stuff that we're going to change, and we're going to see just how far we can push this by not changing the sim, but just changing the materials, the lights, and the render settings, and you know, and then later in compositing. It's going to go pretty far from this. So click on the snapshot so we can consult it later. Press the stop button here if you haven't already. And let's make some materials. Now, as of this recording, it is the way that it is. And in general, you may not be using Mantra, maybe you're using Redshift, or maybe you're using Arnold, or who knows what else, or Karma. What I'm going to talk about is specific to how it is right now, but it is all based on general principles of rendering and shading and lighting. This stuff hasn't changed for a long time, and it doesn't seem like it's going to be changing anytime soon. So when I show you how to do a thing in Pyro Shader, or how to do a thing wherever, just try to, if you're watching this right now in January, you can literally follow along. I wouldn't be surprised if things start to change again. The point is to learn the principles, and then you won't need a video tutorial to tell you how to apply what you learn to a different setup. So without further ado, Pyro Shader, we are using Mantra, so we are using the Pyro Shader. And we also want a principled shader. Principled shader is simply the standard shader in Houdini for not volume stuff. So in this case, our background geometry. So again, if Houdini gets rid of the principled shader tomorrow, don't lose your mind over it. Just use whatever the new shader is. And if the Pyro shader goes away and they call it the volume shader, it'll still have density settings. It's still going to have color settings. It's still going to have a scattering phase, I'm sure. So all this stuff will apply generally to anything that comes down the road. You're just learning the concepts. So anyway, Pyro Shader and Principled Shader. So there they are. So let's put on the smoke, the Pyro Shader, and the Principled Shader. And let's see, what does that get us? Of course it won't be right because we haven't really changed anything yet. One of the first things we're going to want to change is the Principled Shader itself is reflective by default. So you can kind of see some shininess over there. So let's go back to the material area. Also, for the record, in the past we used the material palette sometimes. You can drag the Principled Shader to here. You could have found the Pyro Shader somewhere down here. I don't even know. But it's just as easy, like we make any other node in Houdini, to just make the nodes directly into the matte area. If you make it in the material palette, it is putting it in the matte area anyway. So in any case, the Principled Shader has reflectivity at 1, set it to 0. We're also going to want to have the actual density on this be higher. Remember when we were doing our volume visualizing back here, we said density scale 4, meaning show me in the viewport this as though it was 4 times denser. It's not making it denser, it's just showing it in the viewport 4 times denser. So rather than re-simming with more density, which might even change the sim, as things like turbulence and disturbance can be based on the density values, let's not re-sim it, let's just change it after the fact. So go to the Pyro Shader and just say, let's match that 4 with the density scale 4 here. So now it will look much denser, like so. So very different from here to here already. So we'll snapshot that one. Something else we're going to want to do, because we're going to want to do lots of things here, is the smoke color is saying, yes, tint the smoke color with the CD fields that we made, but it's then scaling it all by 0.2. So make this bright white so that it's scaling it by 1, meaning don't scale it, just keep it, anything times 1 is itself. So now it's much nicer and more colorful. So we're getting closer already. Finally, something that people take for granted is the background of, because smoke is transparent, or it's, semi-transparent. So a lot of the color is what's leaching through from the background. So the fact that the background is so light is what's making this also light. Watch what happens if I make the base color way darker. So I'm not going to click black, I'm going to click like next to black. Look how different that is now. You can see so much more of it now. So I'm just going to let that finish. This is a pretty fast render anyway. So there you go. So we went from this to this. Huge difference. And especially from this to this. It's the same sim. It's just denser. And even changing the background alone to be darker allows this to come through. Because, you know, the brighter it is, the less you're going to see. So much less. You wouldn't think, but it has a huge role in this. So a lot of times, just as a general tip, when you're doing smoke sims, especially ones that you know are going to be kind of thin, you usually are going to want to make them denser than you'd think they should be, because of how different a light background can treat it. It's so different, and all we did was change the color of the background here. So, and this goes for you compositing as well. If you were just rendering out the smoke and you compositing it over a bright plate, meaning bright footage, it will have the same issue. So just so you know. So we got that going. Another thing we can do on the Pyro Shader is the scattering phase. This is a little subtle thing which says, hey, is the material that this smoke is made out of, is it reflective material like dust and dirt and rock and things that are hard particulate that are just very small? They reflect light because they were solid things. Or does it transmit light? Meaning it's positive, like steam. Steam is water droplets. Water droplets are clear. Light passes through steam. This is very important to getting your smoke to look correct. Look how different it is. You tend to get a more uniform look to the scattering phase as being positive, and you tend to get a more detailed look for it being negative. Now this is, in my mind, like a gas of some kind of colorful gas, so let's keep it to the negative number here. So that's cool. It's subtle, but it is real, especially if you do have lights behind this. What's what this is saying? Is the light shining through it, or is it being reflected back away from it? We have only one light coming from the front right now, so we're not going to see as much from the positive scattering phase. For more information about that, consult your local, obviously you can always look at the help card for the Pyro Shader, which may or may not load, but there's lots of little things in here and showing you how the density, all these values, but here's the scattering phase again. It controls if the light is passing through it from behind, or if it's a more solid thing. Cool. So that's pretty much all we're going to do, honestly, on the Pyro Shader. We're not doing anything with fire, so that's about it. So consider yourself lucky with the Pyro Shader. The principled shader, we made it dark. It's not reflective, so that's pretty much it for that as well. So now let's actually talk about Mantra rendering settings. So let's talk about Mantra's rendering settings, although again, keep in mind that most renders have similar settings on them. They just work differently under the hood, and maybe they present it to you differently on the top of the hood, I guess. But a lot of the principles are similar. And again, Mantra is still alive and kicking regardless. So first things first. Click over to the Mantra node. We're talking about rendering, so click the Rendering tab. We can turn Allow Motion Blur on later, but again, it will slow things down considerably, and I don't even know that we necessarily need it for this lesson because things aren't moving that fast. But there it is. I guess we might as well talk about it. I'll pause this. To see motion blur, make sure the node that's being rendered, in this case render smoke, on its sampling tab has on velocity blur. Velocity blur means if your regular polygonal geometry, look for the V and W. W is angular velocity. Look for those attributes to determine the velocity. If you are a volume, look for the vel volume. The vel volume is there. There it is, X, Y, and Z. They came from the sim. So if I turn on allow motion blur, it has to think about it because it needs to redo the whole thing. It needs to actually store that in the renderable thing. So does it look different? I mean, it does. You can see how it's moved a little bit. It got dragged forward a little bit. Is it different? It's not in our case because we don't have strong velocities. Even when we were sourcing the velocity into our scene here, remember we scaled it down by like 0.1 or, scaled it down 90%. So, I'm just going to turn it off. It's not really worth it in this case. But there it is. I mean, many times you will need it, so you should absolutely know about it. Now, the main event, actually, we might as well just start with it, and they have it up front and center here, is the pixel samples. Every single one of these pixels, we can look at them, press I to bring up the inspector here. You can right-click and drag to zoom in if you want, but even if you don't zoom in, the inspector is doing that for us. Obviously, an image is many pixels, but every pixel has a final color determined by something. The ray is passing out from the camera through the image pixel, and then it continues into the scene to find out what color should I be? What color should I be when I grow up? So it sets off into the world to go find out what its destiny color is supposed to be. Now, in fact, what happens is that pixel doesn't just send out one ray. It doesn't just continue as one ray. What happens is this many rays comes out of it. In this case, it says 3 by 3. So it's a 3 by 3 grid. So that one pixel is really subdivided into 9 squares. And each of those are the rays that go out into the world. And then that final, whatever their 9 destinies are averaged together to be the final color. So here's a fun little example, really with just 2 by 2 pixel samples, also known as 4 pixel samples, where we have a camera, we have a pig head, not technically a volume, but just as an easier idea to wrap your head around. And then this is the image that's actually being rendered. And so the way a render happens is there's rays being cast out from the camera, and if they pass through the pixel, and if they intersect something, the pixels record that. So what we end up with is an image. So, but you didn't know, you can make a ray tracer in SOPs pretty easily. So what does that mean? Well, I want to show you specifically how one pixel is made up of these 4 pixel samples, because I'm saying in this case 2 by 2. So mostly blue and 1 red averages out to mostly blue, but with some red, which is purple. So you can see here's just 1 blue and, well, 2 blues apparently, and 2 nothings make a very light blue. And that's what's happening. The nothings are when the ray is missing the pig head entirely. The blues are when the ray is actually hitting the blue from the camera through the image, through the sub-pixel sample, and then it's averaged. And that happens for every single pixel. And that's the thing. So if every pixel needs 4 of these samples, then it takes 4 times as long to render this image because, the ray hits the pig, but then it has to figure out what the lighting is. It has to send rays at the lights, as we'll see later, and do other stuff. So yes, I think you get that. Hopefully that it has to do 4 times as much work, and that's why we need to be careful with pixel samples. Isn't that cool? Yeah, let's just take that in for a minute. It's been a long time making this demo. I want to enjoy it. Yeah, cool. Cool. All right, anyway, so there it is, your pig head rendered to a piece of geometry. Pixel samples. In practice, what that means is that if you put 1 by 1, it's going to render crazy fast. It's also going to look like garbage. So it looks very grainy, super, super grainy. So if I were to, compare it to what it just was, you can see how grainy it was and how thing it is now. You can also see that this rendered in 2 seconds, and that rendered in 17 seconds. So obviously, asking it to do 9 times as much work, obviously makes it take longer. So 9 times the 2 seconds is 18 seconds, which is approximately what we got here. So it's 18 times as much work. And the same goes for if you were to erase it. If we went to 6 to 6, it's going to take way longer because now it needs to do 36 times as much work, at least versus the 1 pixel sample. So as usual, hey, make this as high as you can. It'll always look better. That said, it gets exponentially worse. So it slows down very fast once you get past the default, which is 3 by 3. I often find that I do not need to go any higher than 3 by 3. So don't, if you can, get away with it. There's other settings that will increase the quality of your image without you having to do that. Because, and this is the ultimate thing to know about pixel samples, because it's saying subdivide the pixel into 9 pixels and then shade each one and average it, that means everything else that it's doing, the entire render is being multiplied that many times. Whereas other quality settings down here do not require nearly as much work to be done. If you were, put another way, if I were to increase, let's say, the quality of a thing down here, it's increasing the quality in all 9 samples or in all 36 samples. So anything you do here is being multiplied by this. So don't start with this because it's multiplying the quality of everything. In practice, there's really only 1 or 2 of these things that we need to increase, as opposed to increasing the quality, increasing the work that every single one of these things needs to do. I hope that makes sense. If each one of these things takes a certain amount of work, right, and we only increase the amount of work that one of them has to do, well, then that's only that much more work. But if we say increase everything at once, we might be increasing things that are not actually adding any appreciable improvement to the image. So we want to target where we are spending extra work. I think that's maybe a better way of putting it. All right, so we got density, we got temperature. Temperature is making some velocity happen from buoyancy, but let's actually source velocity into the sim, where these objects are. So they're hot, they're sputtering, they're making smoke fly out of them. So let's have some velocity happen here. So to do that, let's just copy and paste one of these volume rasterized attributes, and we'll use the velocity of the actual particle sim. So you can turn this on if you want to see it, but doesn't really matter. But you can see these little trails. That is the V attribute, V for velocity. And there you go. So we'll type V. Now, what is this? What is that? It's how does that velocity? Well, it's trying to show us, it's trying to say, okay, I have volumes with values in them, and that's what I guess they look like. It doesn't look very good. Actually, first turn off velocity blur. We don't want the trails this time. We don't want to smear that. We don't need to anyway. You could though. We can also put the coverage scale back to 1. We'll keep everything else the same. So what is this actually? I like to do a volume slice. Whing. So now we're seeing it as color. So the XYZ velocity is showing up as RGB. And then trail, or rather volume trail. Take the slice that we just made as the input and the volume that we made as the second input. And now you can see we've got some velocity trails, like so. They're not that interesting, but they are showing the direction that things are going in. So let's start with that. So this is just the visualization. So just keep that off to the side over here. We don't want it to go through this density breakup thing, but we do want it to get down here. So merge them together. Now, unfortunately, it looks like this. We don't want that. So let's use a volume visualizer to define what this looks like. And we can just say the density field is just the density. The velocity fields, which are still here, you can see the v vector velocity field is still there. We just don't see it anymore. We don't have this boxy look to it anymore. The reason why you don't see it over here is that these values are negative. The velocity going to the left in the negative x direction is negative. So it's not showing it as density because they're negative density values. So anyway, just keep this on. And now in here, oops, I'm not on the first frame. Go back to the first frame. This is already set up to read velocity in. So what does that look like? Whoa, crazy. I'm also going to turn off this active area thing. We don't need to see this anymore. We can trust that it is in fact running a sparse sim. So a lot of velocity coming in. It's not wrong, but it's too much. I don't want that much. So I'm just going to say, hey, how about half of that? So definitely a little more under control now. I'm going to say 1/10 of it. Oops. That's looking pretty good. Because I want my streaking to largely stay in place. But now with some velocity and some temperature, it's starting to look cool. Very good. So that's nice. We can noise up our volume as well. There's a few ways of doing this. I'm just going to say, well, we'll look at it this way. I'm going to say let's use a volume VOP again. And we're going to do a noise thing again. But this time, let's actually make sure you hook both of these, or rather, yeah, let's hook both of these into this and this into this. And I'm going to say, in here, let's have the display be on this. Let's find a nice one to look at. So there we go. So jump in here. It's reading the density in. Let's not do that. Let's just grab the one we want. So V is the one that we want. It's a vector type. So now we're reading the velocity volume in. And if we export, bind export, we can export it in the same way. V, which is a 3 float thing. And there you go. From input to output, it looks the same. We didn't change anything. Let us use an anti-alias noise again, though. Anti-alias noise in the same manner as before. Vector to vector 4. We go position, time, input. This time, though, we want a 3D noise to come out the other side of this. And we can say, let us maybe just add that to the velocity. It's only going to do it in the areas where there is velocity in the first place. And there you go. We didn't see much happen though. We can increase the amplitude on this. You can see now it's starting to break it apart. Once again, you know, do whatever you want here to make it look cooler. I'm going to do another frequency of 2 to get the details to be a little bit smaller. I think roughing it up is also good, which it makes it more jagged a little bit. We might even go like twice as high with this amplitude. Yeah. If you wanted to just see what this looked like, we could just not add it. You can see it is going in every direction. But we want to add it so it's still predominantly going in the direction that it was going in. It's just being noised up in addition. And there you go. So now we have a more interesting velocity field. And make sure that that's actually what's being brought into over here. I would just mention also while we're here, there is a node called volume velocity, which is a perfectly good thing to use as well. If you want to look at that, you can see it here. Volume velocity can do things like curl noise pretty easily, like so. Really no reason not to use it. I'm kind of just used to doing it this other way. But it is kind of nice to just use a pre-made node. It just has the similar kind of things under the hood. But you might as well use it. I mean, there's no reason not to, I suppose. Grain it up, change the size of it. It's pretty cool. I just wanted to use it this way. I like to use VOPs and things. But there you go. You got options. So we'll put this one back over here, though. And I'll delete this one. Cool. So once again, it turns the visibility of it off in the viewport, but it's still there. And if we come here, get out of here, Duolingo. I wonder if that showed up on the record. I'm learning German. I've been learning for 6 months now. Anyway, so there you go. So now we can see all that extra volume or velocity that's being thrown into there is making it look really cool now. So that's cool. For some reason, even when you have the like high quality lighting with shadows on, it doesn't show up in the dynamics mode. I don't really know why. So if we dop import fields, which you'll recall from the earlier lessons, we can say this is the dop network we wanted, the smoke object is what we wanted, and choose smoke from here. And now it imports those fields back out, and now you can see the shadows on it. So again, if you go in here, we lose the shadows. I don't really know why that is. So that's cool. We also lose our visualization settings and things. I mean, this one creates some new ones where it says the velocity is invisible and we're only seeing this density of smoke. But it can be nice to make our own volume visualizer. And then we can like play with the density some more even. So if I say this is density, I can, you know, scale it if I want to. It might look nice like this. Scaled to 4. So we're really getting somewhere now, aren't we? Cool. Okay, unfortunately Houdini crashed, so I have lost all my beautiful progress pictures, but Say Libby. So anyway, the last thing, like I said, was now we have an all CG scene here. You know, CG smoke, CG background. Sometimes you don't have, you know, we wanted to just have this smoke, let's say, live in a actual scene that was shot on film. So, you know, we wouldn't have this background. We would just have footage back here. What you would do in that case is you would still have to model geometry that represented your scene, and, you know, let's say your ground, for example, because we still need to receive shadows and things onto it in order to, you know, make it feel like this actually lives in the live action scene. So it's pretty simple. What you can do is those image planes we talked about earlier. So on the mantra background one like this, we can create another image plane that will store shadows. Basically, just create a new image plane and say a direct shadow matte. The direct shadow matte will say that for, you know, every object that's actually being rendered, the ground, just also store, like when it's sending out shadow rays, it knows that it's doing that. And so it's just saying, write the results of that into this other image plane. So it'll still do it in terms of the smoke here. So to show you what that looks like, we render the background mantra thing here. And let that get started. It'll probably be pretty grainy in our low quality settings here, but you know, you can always pump up the settings and stuff. So if we look at direct shadow, oh, that's not it. There we go. This is basically the opposite. Everywhere that it's lighter is where it will need to be made darker. So you can see, looking at it, that's where the shadow is. You can also see that this is all fairly dark back here. It's all kind of in shadow. And that's what this is showing us. So you would take this image, I mean a less grainy one, of course, but you would use this image to use in your compositing, where you have your live action footage, and you would use this to like subtract this much color out of your live action footage, or you would invert this to turn this back into dark, and you'd multiply this by your live action footage to again create shadows, you know, good enough shadows. You know, relies on you modeling again what's going on in your live action footage. But, you know, we're not doing that in this lesson, but I think it's a common enough thing you might want to know how to do that, yes, it's just another image plane we can store in our output images, and you can extract this direct shadow in Nuke or in Houdini, as I'll show you in the next chapter, and that's how you would do it. Along those lines, we don't need the indirect lighting here, because the indirect lighting was only for the volumes. They're the only ones, you know, we increased the volume limit up, so only that was getting indirect lighting anyway, so we don't even have to worry about that. So you just turn that off, make your file size smaller. Yeah, everything else is fine. Cool. So it's also worth noting, it's a similar thing here. The individual lights get their own contributions here. I mean, obviously there's not much to see for the geometry light. I guess there is a little bit if you really heighten it, but okay. So that's enough. Yeah, so that should be it. Before you send off, you know, a huge render, I would say spend the 15 minutes or 20 minutes, or hopefully not an hour, on doing one frame of the smoke here, like in the regular, not preview thing. So let's actually go to HQ mode. Let's actually render one frame of the smoke into MPlay and just look at it. Because again, this is what will be rendered. This will probably take some time to do, but we might as well invest one frame's worth of time into seeing what it's going to look like when it's over. I want to make sure that the detail is there, that something crazy isn't happening. don't worry about tweaking like how bright the light is or anything. That's exactly what we're going to do in the compositing. But we can see we do have so much detail in here already, which is nice. We don't really need to resim our sim at a higher setting or anything. So I'm sure this will turn out fine. But just for us as a sanity check, run one frame, and then once we're confident that it's looking fine and that the render settings are good, then we'll send them all out. So I'll let that finish and we'll reconvene and then we'll go away again. And there you go. Took 7 minutes on my computer for probably one of the longer frames towards the end there. And yeah, looks really cool. Lots of nice detail. Everything seems good. No graininess in the alpha. You know, a little bit of graininess over here still. But, I mean, you know, it's pretty good. Whatever. Lots of nice image planes to look at if I could ever get it to open. Yeah, that's cool. Yeah, sweet. So there it is, ready to go. Close that. If you want to test the other one, you can. The background one. I mean, the background one is just the friggin', you know, wall. So it should be fine. But I guess, let's see. In any case, so we're going to render these out now. All those image planes are stored in the EXRs. So, oh, see, look at that. Good thing we tested it. So, running this, when we duplicated our mantra nodes here, that didn't duplicate the overrides. So, we had all these cool overrides for the high quality render on the one node, but they're not on the other node. So, there you go. Very important that we do these tests. So, now that we're doing it, turn off the override camera resolution, come back over to the thing over here. I think we just need to, the noise level should be 0.01, the stochastic should be 8, and I don't think we really changed anything else. Oh yeah, well, there was the limits, but we don't need a limit for the ground. I'll just include this for fun. So one more test on the background. See, look at that. Sanity checks. That would have been annoying. Find out that I had 120 frames of a half resolution noisy ground. Not that they take that long to render anyway, but still. So obviously this is better now. And there you go. And there's our direct shadow that we're not going to use. Still kind of grainy actually on the direct shadow. Well, whatever. So good, done with the rendering and simulation, all that stuff. The last thing is to actually render these out now and then composite them together, and that's actually pretty fun and easy. So I clicked on the purple button here on the merge, do node by node on here, render, and that's it. It'll take a while. See you soon. All right, so here's our render. Looking pretty cool. Lots of detail, everything was working. We can also look at the individual layers. I already preloaded these images, meaning I played through the mplay. Yours may not play quite as fast the first time, but that's okay. Yeah, direct light, indirect light, all that stuff we talked about. The geom light, the geom light direct is pretty cool. Yeah, that's rad. You can see all the shadows, like beams of shadows almost. You can see the angular shadows kind of in here. Pretty rad, you know. So we'll actually end up compositing these elements together, making changes to these, and we'll end up with something like this, but with whatever changes we make. We also have this super cool element, which is just, you know, this. But you get the idea there. That's cool too. Pretty sweet. Yeah. So let's actually composite these elements together. So I already know that we're going to want another one of these planes. I haven't turned on the indirect light yet, but let's just add indirect to here. We also want this to do it per light. And if I render it right now, just saying indirect there isn't going to do anything. So, and the indirect contribution is nothing because it's not actually on. Indirect light means when we keep talking about the ray comes from the camera, it it lands somewhere, and then that somewhere looks at a light, and then it says, okay, I'm this bright now. What indirect lighting means is once that direct light is figured out, like our ray landed here and it said, this is how bright I am, other parts of the volume can now be illuminated by that lighting. So the fact that this area is now bright because it's in the sunlight, areas that are in shadow nearby that otherwise were not getting lit might be getting lit by this now bright part of the volume. That's indirect light, also known as bounce lighting and many other global illumination, 100 other things people call it. But essentially, indirect light is what we're calling it right now. It is very, very expensive. There's lots of ways to cheat to get approximate looking light that's pretty good that some people engineer. Mantra doesn't really have a cheat way of doing it, so you kind of have to do it the direct way. And that is, and this will slow your render down quite a bit. Under rendering limits, if we were dealing with regular polygonal geometry, we would turn the diffuse limit up to 1. Because we're dealing with volumes, we're going to turn the volume limit up to 1. So now your render will take longer, this is why we need to really go back and look at the sampling and being like, oh, I don't know, where can I save some time? Maybe I'll bring the volume quality down or whatever. Or maybe I don't need quite as many stochastic samples or whatever. But in any case, so we went from 11 seconds to 18 seconds. It increased it by like 70%, 80%. But it feels so much better. It's probably pretty subtle. I know it's very silly as I go back and forth between these two. And you just see like, oh, it's a little bit brighter. Yeah, but it's only a little bit brighter towards the top. And it just feels like light is filtering through this. Again, especially by this light over here. So let's actually see it. Now we'll actually have it. The end light indirect is this. This is all this secondary lighting that got calculated. The direct lighting was this. And then this was all the extra light that essentially filtered out into the volume. Denser areas, will block the transmission of light, but will itself be brighter. Obviously, the end light or the geometry light indirect, we'll have a look to it. I mean, we have all these like fireflies and things right now because our render quality is so low. But if I were to do an HQ render here, it's going to take longer. It's going to take a lot longer because the image is now 4 times as large and our various quality settings are such as they are. This is where you might need to push the sampling quality higher on maybe just the geometry light. So this is going to take, this might take some time. It's only technically 2% done. These renders might take, on my computer, this might take 15 minutes to actually finish rendering. When we're working in production on a movie or whatever, we send these frames out to 100 frame shot. We'll send it to 100 computers. Each one will take 15 minutes to do it, so it still takes 15 minutes. So sucks for people at home that obviously only have access to one computer. But that's how we get very good images when we have access to crazy render farms and stuff. I mean, of course, we can make crazier looking stuff. So don't be too discouraged at how much this can slow your computer down. You can still render this for a couple of days. Maybe on the weekend, just let it render for a couple of days and you'll get your 120 frames back eventually. But you can see, obviously, it's more spread out. It's not as drastically horrible as this. That's just the way it goes. So anyway, environment light indirect, same thing. Environment light direct. The sum total of all of these things will be the final image here. So I'm not going to wait for this, but you get the idea. So yeah, image planes are how we're going to tweak these things separately in the compositing step, and the volume limit is getting that really nice bounce lighting that makes things just look so much nicer. Just you can just feel the like large, swathier areas of light bouncing around in it, especially when these things are in motion. You know, it'll feel very nice. It's really a shame because this is so slow, but it is so important to getting it to look good. It's like if you've heard of subsurface scattering for skin, like when you shine a flashlight to the back of your ear, your hand, and you see it's red because the light is passing through your body. That's important to make it feel real and alive, because that just is simply how light moves around. And it doesn't care how expensive it is for your computer to render. All right, one thing I would say though, if you really want, let's say, the scatter from certain lights but not others, that is something that can be arranged. Now, I have to stress, you do want the scattering from this environment light. In this case, sometimes it doesn't really matter. If you have a very thin smoke that's just like outside, so it's just getting blasted by light from all directions, your environment light indirect might just be like, it's just the same thing again, just brighter, but it took forever to calculate that. You can actually disable certain lights for making that contribution. So it'll just overwrite that one. What we can do here, a little known thing, is light contributions. Every light has it. Turn it on and say, hey, the indirect lighting, I'm talking to you, indirect lighting, don't do it. So it's weird, we added a thing and then turned it off, but it does in fact disable that contribution. I mean, you can disable any contribution on here, but that's how that works. So this will now be much faster. It is the environment light indirect volume limit scattering that is taking so long. And it is just for a subtle effect, but it's a subtle effect that's well worth it. So now, if I compare this to this, you can see it's gone away. The geometry light indirect is still there, but the environment light one is not anymore because we turned it off here. And if we turn it back on, it would just come back and be no different, as if we didn't have this here at all. So there you go. That's a little pro move thing for you there, for Mantra again anyway. I imagine a lot of these things will transfer into Karma as well. But in any case, like I said, whether you're using Mantra or not, keep in mind that environment lights scattering is going to be very slow. However you want to turn it off, you can. But if you can't afford it, keep it on, because ultimately your render will look better. Cool. The last thing I'll just mention real quick is with that on, this is the kind of thing, again, that maybe we want this to be off while we're doing our sample. Like, when we're doing our iterations, we might just want to turn that off. So I'll just turn it off here, and in the main take, we can make sure that it is on when we're doing our actually high quality rendering later. Great. And yeah, unfortunately, as I started to mention earlier, motion blur, we've had this off because it's letting us render faster. If you have to have motion blur and the volume limit thing on, it can really slow it down even more. So again, it's not unusual for us to render frames on our render farm where an individual frame might take 45 minutes to an hour per frame. And so for you at home, 120 hours sucks. But you could, even 120 hours, you could just let your computer render for a week and you'll end up with a pretty sweet looking image. Just make sure that, you iterated it on the lower quality settings first so you know it's going to look right. All right, enough doom and gloom. Let's get to the next thing, which is some fun rendered tweaky stuff. All right, so the actual sim can just live in here too. I mean, we have our particle sim up here. We can just put our pyro sim down here. So make a dot network. Have this go into that. We'll call it like, pyro net. Like a cool cyberpunk thing. Nothing in here, not like the particle one last time. So let's make our type sparse. Like so. And we want the pyro solver sparse. Type sparse again. We want this smoke object sparse. The original ones are still in here. If you typed pyro, you'd have pyro solver and pyro sparse. The sparse solver doesn't completely replace the pyro solver. The sparse solver is great when you have things that are sparse. Like we're going to have these trails with huge gaps of air between them. Explosions in general would also benefit from sparse because they tend to, let's say it's like a mushroom cloud, you have a lot of area under here that's not filled in. The sparse solver will usually be faster. Let's just go ahead and hook these up. It will, but the original pyro solver still works fine, and it actually is accelerated with OpenCL, which is the thing that uses the GPU cores together with your CPU to do stuff together, which is nice. The sparse solver actually doesn't support OpenCL, or at least it doesn't with the sparse capability. So, turn that off again and have this be on the left side. Sorry, I'm like saying and thinking two things at the same time. I'm just trying to say there are reasons to use the old pyro solver still, although most of the time you will probably want to use the sparse solver. It's pretty fast. Let's see what we get. Let's do a volume source and start bringing in what we created, and we can start to see what makes the sparse solver different. So go to sourcing, which apparently is the third one here. And we have our volume source here. Say the first context geometry, which again is this input, is our input. And we need to switch away from source smoke and then switch back to source smoke to actually get it to populate these things here. We have a density field. We don't have a velocity or temperature field, so only the density one's going to do anything. So we press play. There you go. So we can already kind of see, oh look, we didn't even have to set up the dimensions for our smoke sim. Remember we had to do that before in volumes 2 with the regular standard pyrosim. It will automatically resize the maximum bounds for us. That's cool. But even better than that, if we have a frame like this, not only did it resize to this, it's actually only simulating the areas right around that. How do we know? There's a guide on the smoke object called active region. If it looks super dark like this, go to smooth shaded, and then it'll be bright again. This is actually the only region that's being stored in memory. Everything that's in this jagged blue area. So it's not even that it's simulating everything in this white box. It's only simulating everything that's in these blue areas. which is obviously a massive improvement. There is, in fact, I think, just looking at this, more unused area in here than used area. So only this needs to be stored in memory, and only this needs to be actually simulated. Normally, the fluid simulations like this, because smoke is a fluid, has to do these huge matrix calculations to figure out the pressure and whatnot. And now it will do it only in these little smaller areas. So we have it. So where is it? It's where the smoke is, and then it's expanded a few tiles out. These cubes are tiles. So that's pretty cool. Go to the pyrosparse, turn off this dissipation. We'll make our own microsolvers. But there you go. Here it is just accumulating. So this is more usually what your sim will look like, where it's not necessarily broken apart simulation areas, but it's still, it's one continuous area now, but it's still getting away with not doing all of this area, all of this area, all of this area. It's a huge, huge win. Even all of this area, looking at it from the top. So again, it's practically doing half of the work than it would have had to have done otherwise. Why might you still want to use the old pyrosolver? One of the main reasons could be if you're going to just have everything, if you just have, let's say, a whole scene of smoke, like you're in a room where, there's like knockout gas is coming in or something, and you're just going to have smoke everywhere, it can be more efficient to not use this. Because again, this doesn't use OpenCL. If you turn on OpenCL, there is an option for it, it will throw an error and say, hey, listen, you can use OpenCL, but I'm not going to do the sparse solving anymore. Sparse solving is not supported with OpenCL disabled. So it'll still do almost like a regular pyrosim. So there you go. So if you want to use OpenCL, you're going to want to use the regular pyrosolver. So that's a big reason to use the regular pyrosolver, which is why I'm not going to call it the old pyrosolver. It's just the dense pyrosolver. This is the sparse pyrosolver. Similarly, if I had like a ship coming in, let's say from over down here, like a big meteor is coming in here, normally in the standard dense pyrosolver, it would be pushing all of the air in front of it. But if I have a collider in here, unless I add that to the sparse sim explicitly, it doesn't know about anything happening out here. So I could have a big ship moving in here thinking that it's affecting the velocities, the air being pushed ahead of it, but it won't be because it's not in the sim. And you can explicitly add it to the sim, but then again, you're starting to lose the benefits of it being a sparse solver. And if you're not taking advantage of the sparsity, then it might actually end up being less efficient than the dense solver. But again, to reiterate for the 100th time, much of what you're going to be doing these days probably going to benefit from using the sparse solver. So this certainly does, so we'll just keep doing this. So we talked about that to death. We might want to add temperature into this, and we don't have a temperature field, but we can just reuse our density field. So I'm going to say density. Actually, before I even do that, I did want to show you something else, another little fun gotcha. Sometimes, especially at a higher resolution, so here I am going to 0.02, watch what happens. Well, that sucks. Obviously, we know that this doesn't just stop here. It's supposed to go much higher up. What's happening? Well, when this is at its normal size like this, the tiles themselves are bigger. So the expanded area is bigger. So any given frame, when we source our next bit of volume, we're sourcing our next bit of volume into an active region. That's good. So it sees it and then expands it more. So our density is being added always into an active region, and it's allowed to expand just in time to always be accommodating the next bit, and there's no issue. But when our voxels are small, the tiles are smaller. Again, the blue cubes are the tiles. but our particles that are sourcing are still moving as fast as they've ever been moving. So what's happening is it's trying to source here, 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 but it's not sourcing into an active region. So it's not being seen. So that's why it's broken. All that is to say, always have enlarged fields to contain sources on your volume source, and their problem immediately goes away. What does that mean? It means when it tries to source into a non-active area, simply make that an active area. This should pretty much always be on. I don't know why it's not on by default, but that is a gotcha for you if you're trying to get your feet wet with the sparse solver and you don't know what that is. So now you do know, which is why you're watching this lesson, and there you go. So now it will always work, and that's awesome. So I'm going to go once again back to the big voxels though, just so we can work quicker. Temperature, let's just use the density, incoming density field as temperature. So now we can see the buoyancy of the heat making it go up. It's going up quite a bit. It's quite hot because when we made this source on here, we said everything is times 10. So the voxels themselves, their highest values are probably around 10. So the temperature is also 10. That's quite hot. So what we can do is we can just say, let's multiply it by 0.1 on the way in. So we're still getting the full density, but the temperature is only going to be 1/10 of it. So you can see already immediately, it's not moving nearly as much. It's still moving though. It's still adding a nice bit of extra motion to give you the sense that whatever's emitting this smoke is like some super hot little thing that's then, the buoyancy is making it go up. So there you go. So that was a good chapter, right? You know about the sparse solver now? Pretty cool.